boom, 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 boom. Chemistry 3101, Organic Chemistry 1. Chapter 3 deals with acids and bases. And many of the people who are in this class right now are coming out of General Chemistry 2. And in General Chemistry 2, you spend a lot of time talking about acids and bases. And thus, many of the concepts you'll see in this chapter will be a continuation of what you saw in General Chemistry 2. However, since we're going to be looking at it from the point of view of organic chemistry, there's going to be plenty of new content in here as well. But let's start with a little bit of a review of what a Bronsted, Lowry, acid, and base are. And this is a definition that you should have learned in General Chemistry 1, and you should have seen it in General Chemistry 2 as well. And let's just review it. It says that a Bronsted acid is a proton donor. It says here that a Bronsted-Lowry acid donates a proton. If you think about something like, sulfuric acid. Well, what does sulfuric acid do? It donates a proton. It's an H+ donor. And if you're wondering, why do we call a hydrogen ion a proton? Well, if you think about it, what is a hydrogen atom? A hydrogen atom is just one proton and one electron. And so if you rip off the electron, you just end up with the nucleus, which is nothing more than a proton, and that's why we call H+ a proton. So acids donate a proton, and a base accepts a proton. You should have the strong acids memorized from General Chemistry 1, so we can just scribble those down as a reminder. Strong acids, and you'll learn a few more strong acids in this class. The strong acids from General Chemistry 1 would be sulfuric acid, nitric acid, chloric acid, what else? Hydroiodic acid, hydrobromic acid, and hydrochloric acid. So those are the strong acids that you would have seen in General Chemistry 1. And again, all of those are proton donors. So let's see here. Recall from General Chemistry this classic example. If you put HCl, hydrochloric acid, and you put it in some water, what happens is the acid is going to donate this proton to the water to form hydronium, which is H3O+. So just a reminder that H3O+ is an ion called hydronium ion. And of course, you would end up with chloride as well. And not only do you have to be able to identify the acid and the base, as they're shown right here, but you also have to be able to identify the conjugate acid and conjugate base. Thus, you need to understand that when the acid loses its proton, what you're left over with is the conjugate base. When the base accepts a proton, what you end up with is the conjugate acid. And oftentimes we refer to these as acid conjugate base, base conjugate acid pairs. You need to be able to identify these. They're definitely going to come up on quiz 3. Now, if you ever get confused as to which one is the conjugate acid and which one is the conjugate base, what I would do is I would think about the reaction going just in the reverse direction. Of course, this is an equilibrium to some extent. However, if you think of this going in the reverse direction, what is the hydronium ion doing? If you go in this direction, what it's doing is it ends up losing a proton, therefore it's a proton donor, which means it is an acid. Conversely, if you look at the chloride ion and you're going in reverse, what's happening is that it's gaining a proton, and a base is a proton acceptor, and thus chloride is the conjugate base. Again, if you're ever struggling identifying the conjugate acid and conjugate base, just think about the reaction in reverse and ask yourself, what are these species doing? And you should be able to identify the conjugate acid and the conjugate base. Kind of backing up in history here a little bit, you might remember that there's another definition of acids and bases that you would have learned before the Bronsted-Lowry definition, and that is the Arrhenius definition. So if we go way back here on the introduction, or sorry, the title slide, you might remember the Arrhenius definition, that an acid was something that makes H3O+ in water, and a base is something that makes hydroxide in water. And again, that's historical. That was the first kind of definition of an acid and a base. And of course, the problem with this is if you take something like ammonia, well, ammonia doesn't have hydroxide in it, like sodium hydroxide or lithium hydroxide. And that is why Bronsted and Lowry had to broaden the definition of what an acid and a base is. And again, from your general chemistry 1 and 2 days, you should remember that there's also something called a Lewis acid and a Lewis base, which broadens this definition even more. However, for most of this chapter, in fact, probably more than half of it, we're going to be focusing on Bronsted-Lowry acids and bases. All right. It says here that the conjugate acid, another way of framing it, is what results when the base accepts a proton. A conjugate base is what you end up getting when the acid gives up a proton. Let's see if we can label the acid, the base, and the conjugates down here. If I call these 4 species, if I call them A, B, C, and D, could anybody identify what is the acid and what is the base? Let's start with A. Would A be the acid or the base in my reactants? Would A be the acid or the base? Yeah, it's the base, right? It's definitely not the acid, because if you look at what's happening in this direction, who's donating a proton? Water is donating a proton because you're left over with hydroxide in the end, whereas this thing here, which is what we call an alkoxide, that is accepting this proton here. And if we go back to the definition of what a Bronsted base is, it's a proton acceptor. And so we'll put here, this is the base. Again, it is an H plus acceptor. And if A is the base, that means that water in this case is the acid. Oops, it is the acid. And why do we know that? Because it is the H plus donor. It's losing this proton that's highlighted in red. Now, if we look at C and D, we'll just start with C. Could anybody tell me, would C be the conjugate acid or the conjugate base? Would this be the conjugate acid or the conjugate base? Yeah, definitely. Yeah, it's the conjugate acid. All right, so let's scribble that in here. We'll put conjugate acid, which means that the hydroxide must be the conjugate base. All right, and how did we figure that out? Well, there's a couple of ways. You could know the definition that the conjugate acid is what results when the base accepts a proton. And since this is our base, it accepts a proton, and that must be our conjugate acid. You could also remember that the conjugate base is what results when the acid gives up a proton. Here's our acid, it loses a proton, you get hydroxide, ergo, it must be the conjugate base. Another way to think about it is, if you can't remember that definition, is just going in the reverse direction. You can see that this species, this alcohol, is losing a proton to give us this alkoxide. And you can see that, oops, the hydroxide is actually accepting a proton, therefore it must be a base. Good. And again, this is definitely going to come up on your next quiz, having to identify an acid, a base, a conjugate acid, and a conjugate base. Very important. Again, this is something that you would have seen in General Chemistry 1 and also in General Chemistry 2. And now you're seeing it in Organic Chemistry. It just won't go away, will it? All right, well, let's move on from there and let's talk about curved arrows in a reaction. You know, if we go back to chapter 2, we spent quite a bit of time looking at curved arrows, didn't we? However, when we looked at those curved arrows in chapter 2, what were we talking about? We were talking about curved arrows that we use to make resonance structures. We were not actually showing any kind of physical process. We were not showing any reaction whatsoever. We were just showing delocalization of electrons, but now we're going to be talking about using curved arrows in reactions. Completely different from chapter 2, in which we didn't look at any reactions at all. We just looked at how electrons were delocalized around a molecule or ion in order to show all the contributors to the overall resonance hybrid. Now we're actually going to be showing making and breaking of bonds. We're going to break bonds and we're going to make bonds, and we're going to use curved arrows to show the flow of electron density. If you go back to the first day in Chemistry 3101, and the first chapter, introduction, what I said is in organic chemistry, you have to focus on the electrons. And if you remember from general chemistry, you spent basically an entire year talking about valence electrons because those are the electrons that are involved in reactions. We only spent a few, maybe a few hours in the classroom talking about nuclear chemistry. And again, we need to use curved arrows to be able to understand reactions in organic chemistry. Check out this reaction right here. You see where you have this B minus here? If you're like, what is this thing here? That is just meaning it's some kind of generic base. Okay, so B for base. It's got a lone pair. It's also got a negative charge. And then HA, that just represents some kind of generic acid. It might be HCl. It might be HBr. It might be HF. It might be acetic acid. It could be any acid. So we'll just put acid of some kind here. And what the curved arrows are showing here is the flow of two electrons, but you can see that the pair of electrons on my base is going over to the hydrogen atom here. And what that's doing is it's forming a bond. So that yellow or that red arrow that I have highlighted in yellow is showing a bond being formed. So we would say here, we'll say that's making a bond. And then the second curved arrow starts on the pair of electrons between the hydrogen and A, which would be the conjugate base, of the acid. Anyhow, what you're doing here is you're making and breaking a bond. So we're breaking a bond here. And then where does that pair of electrons end up? It ends up on the conjugate base of the acid. These are the same as the curved arrows in resonance structures, except here they're actually describing the physical movement of electrons. And check out this last bullet point here. Is this a heavy hitter or what? It says learning how to draw mechanisms in organic chemistry is one of the most valuable skills in this class. Let's put a star by that. I cannot stress enough how important it is for you to take a pencil and paper and draw curved arrows. The only way you can understand them is by learning to draw them yourself. Now we're doing this course, these lectures remotely, and so there's not a lot of opportunity for me to walk around the classroom and say, hey, Andrew or Tracy, let me see your curved arrows. How does it look? So more of the onus lies on the student to actually try drawing curved arrows at home. But if you send me, so you're practicing your curved arrow mechanisms and you're not sure if it's correct or not, don't hesitate. Send me a screenshot, send me a picture, and I can take a look at it and make sure your curved arrows are reasonable. And we're going to practice some this morning, curved arrows in reactions. Let's take a look at this very specific example here, and let's go over some terminology or some lingo, so to speak, that I'm going to use in this class. We have a base reacting with an acid. We form a conjugate acid and a conjugate base. And this first curved arrow, what we would actually say is that the base attacks the acid. The base is attacking the acid using a pair of electrons from the oxygen. And the acid cannot lose a proton without a base taking it. Okay, an acid cannot just donate protons into nothing. Okay, somebody has to accept it, and what is going to accept it would be a base. Notice that all acid-base reactions occur in one step. So not only does the base attack the acid, and we form a bond, right? We end up forming a bond, which is one of the bonds in water, but we end up breaking, where's my green highlighter? We end up breaking this bond, and we put a pair of electrons on this oxygen to render it negatively charged and produce our conjugate base. Check out this last bullet point. It says the mechanism shows two arrows indicating that two pairs of electrons move simultaneously. One bond is being broken, the other one is being formed. Again, this is something that has to be practiced. It cannot be just read about and studied, or you can't just watch a video and learn this. We'll put here must practice curved arrows in acid-base reactions. Very important. Okay, well, let's take a look at an example here. It says all the following acid-base reactions. Well, there's only one on here, but I have a couple more that we're going to take a look at after this. All these are reactions that we will study in greater detail later on, some in organic chemistry 1. In fact, I think all of them will be studied in organic chemistry 1. Anyhow, it says for each one, draw a mechanism, then clearly label the acid, the base, conjugate acid, and conjugate base. First thing I'm going to do is put in all the lone pairs. Let's start with that. So I'll use my red pen just to highlight them. On my alcohol here, I need 2 lone pairs on the oxygen because we know that when oxygen has 2 bonds and 2 lone pairs, it has no charge. On my hydroxide ion, excuse me, we know that when oxygen has 1 bond and 3 lone pairs, it has a negative charge. Same thing with this oxygen here. It's got a negative charge, so we need 1, 2, 3 lone pairs. And lastly, on the water, we'll put 2 lone pairs on it. So now we've got the lone pairs on everything. Next thing I want to try with you is to quiz you again on acid, base, conjugate acid, conjugate base. If I call this A, B, C, and D, could anybody identify the base in here? Would it be A, B, C, or D? Which one would be the base? Exactly. Tracy, Andrew, Angel, all 100% correct. This is our base. Yes, absolutely. And that means that A must be our, excuse me, must be our acid. So we'll scribble that in, still delete these letters. Now, what about C and D? I'll ask you, which one would be the conjugate acid? Would it be C or D? Conjugate acid. Absolutely, Andrew. Yes. Yes. And again, I know some people are typing in the chat. If you don't have the chat function on your device, do not hesitate to unmute your mic and just yell out an answer at me. This is a safe space. Never be shy to answer a question in Mr. Dion's classroom. Absolutely. You're all 100% correct. This is our conjugate acid. I love it. That means that this is our conjugate base. Okay. What were some of the things that we learned about curved arrows? When you're drawing a curved arrow, okay, the tail has to start on a pair of electrons, okay, and then the tip of the arrow is going to end up, on a nucleus, okay, so on a nucleus, we'll put here, yeah, just nucleus, where do you find a nucleus? On an atom, in an atom, sorry. Anyhow, let's take a look here. So we've got our acid and our base. What's going to happen is the base will attack the acid. Base is going to attack the acid. Let's draw what that would look like. We're going to start with the tail on one of these 3 lone pairs. It could be this one, it could be this one, it could be this one. It doesn't matter. Let's just start at the top. And we're going to start with the tail here, and we're going to end up on a nucleus. Well, if the base is accepting a proton, it's going to accept this proton because you see it's gone over here. So we end the tip of the arrow next to the hydrogen atom. Again, we start on a pair of electrons, and we draw a curved arrow like that. We end it right on the hydrogen atom like that. Well, since hydrogen cannot have 2 bonds, right, because this first arrow represents making a bond, well, that means we're going to have to break this bond. So if we're going to break that bond, we're going to start with the tail on a pair of electrons. The pair is in the bond, and the tip of the arrow is going to end up on the oxygen atom because you have to have a 3rd lone pair on there. And there we have it. Those are the curved arrows for the reaction. We've labeled the conjugate acid and the conjugate base. All right, now I know we're still pretty early in the lecture here, but I want to go and take a look at another question here. So this is something I drummed up for class. It says here, label the acid, base, conjugate acid, and conjugate base. So let's start with this reaction here. And so I have a ketone plus the hydronium ion. Then I end up with this thing here, which is an oxygen with a positive charge. We call that an oxonium ion, and water. So I could call these A, B, C, and D. I noticed that I left out a few lone pairs, so I'll put those in. Put in 1 lone pair, didn't I? Anyhow, let's just scribble them in here. So this oxygen has 2 bonds, needs 2 lone pairs. This one is good. Then if I have an oxygen with a positive charge, it's got 3 bonds and 1 lone pair. And then my water, I don't know, let's just draw out the whole Lewis structure of water. This is organic chemistry. There we go. That's a little better. Okay, so going back to this reaction, if I look at A and B, and again, no trick questions in organic chemistry. I would never try to fool you. Could anybody tell me what would be the acid or the base? Would it be A or B in this reaction? Which one would be the acid, A or B? Yeah. Yes, absolutely. Tracy, Clinton, Andrew, all of you, 100% correct. Angel, yes, perfect. Okay. Yes, this is our acid. Just scribble this out of here and let's throw this in here. This is our acid. Why? Because it donates a proton. In the end, you're left over with water, which must be our conjugate base. So we'll put here acid, conjugate base, and then we'll put here, this is our base, and this is our conjugate acid. Okay, so now what are we going to do? The base is going to attack the acid. Right? What's a base? It's a proton acceptor. What's an acid? It's a proton donor. The magic is going to occur between a pair of electrons and a proton. So let's start with our first curved arrow, which is going to start on a pair of electrons on the base. And you can see that you end up forming this bond right here that I have circled. Well, let's start with the tail on a pair of electrons here, and we're going to grab a proton. So that is this bond that is formed right here. That is making that bond, right? The arrow shows the flow of two electrons, these two electrons, to make this bond. But we know that hydrogen can't have two bonds, and we also know that the oxygen in water has two lone pairs on it. Where does the second lone pair come from? I break the bond between the hydrogen and the oxygen, and I put a pair of electrons on the oxygen to make my water molecule. Give me a thumbs up if you follow me on the curved arrows, and stop me if you have any questions, because we're going to try it one more time. Okay, great. Yeah, awesome. Awesome. Well, let's take a look at another one. Let's just go down here. C. Excuse me. So I wrote this one in red. Anyhow, let's, what if I label these A, B, C, and D? I'm sure you're all getting the hang of it by now. But let me just ask you, which one would be the conjugate base? A, B, C, or D? Conjugate base. I'll throw that out there to you guys. Yeah, absolutely. Yep, perfect. So this is my conjugate base. All right, I'll just erase the rest. Therefore, this is my conjugate acid. This is my acid, and this is my base. So what's going to happen is the base is going to attack the acid. You can see that this proton is not here anymore. So that's the proton that gets transferred over to the water molecule. Well, let's do it. Let's start with putting a curved arrow. We start from a pair of electrons on the hydroxide, and it's going to attack the proton on the acid. We know that the hydrogen can't have two bonds, and so we're going to have to break this bond, and we put a pair of electrons on the oxygen, and just like that, we're done with our acid-base reaction arrow mechanism. So again, these curved arrows actually show a bond being broken and a bond being formed simultaneously. Pretty cool, huh? Okay, let's go back to the slide deck. Let's see here. Somewhere around here, question 3.1. And let's move on and let's get into a little bit of quantifying acidity. So a little bit of math, not a whole lot of math. In fact, there's very little math in organic chemistry, or that you need in Organic Chemistry 1. And this will be a little bit of a review from your General Chemistry 2 days when you learned about equilibrium constants. I'm sure you all learned, if you have, something like A plus, getting ahead of myself here, aren't I? A plus B in equilibrium with C and D, you would have learned that K equilibrium is equal to C to the power of C to D to the power of little d over A to the power of A and B to the power of B. That's something that you would have learned, again, in General Chemistry 2 in the equilibrium chapter. And we used equilibrium constants in General Chemistry 2 to predict whether the reaction favored reactants or products. But here we're going to use it to quantify something called Ka, which is an acid dissociation constant. And then we're going to take the pKa, just like you would take, calculate pH. Anyhow, so quantitative strength analysis, we use numerical data to compare how strong acids are. And what's great about numbers is numbers don't lie. They don't tell lies. And so if you can actually quantify an acid strength with a number, you can hitch your wagon to that and nobody can argue with you. It says here, if you take an acid, Ka is the acid dissociation constant for that acid dissolved in water. It's a measurement of an acid strength. It should say when water is the base. It shouldn't say what water is the base. It should say when water is the base. Anyhow, because we have HA, which is our acid, we have water, which is our base. This is our conjugate base. This is our conjugate acid over here. And if we write out a K equilibrium expression for this, we put the product of the concentration of the products divided by the product of the concentration of the reactants. However, we can factor out water. We factor that out because the concentration of water remains pretty much constant. It's around 55.5 molar. Anyhow, and we end up with this expression, which is Ka. So Ka right here, okay? Now, if we have an acid that's strong, would the Ka be bigger than 1 or smaller than 1 when we have a really strong acid? Could anybody answer that? This question down here. Strong acid, would you have a high Ka or a low Ka? High Ka or low Ka? It's going to be a bigger Ka, right? So stronger acid, the stronger your acid, the higher your Ka will be. All right, think about that. What is the function of an acid? An acid is a proton donor, right? H plus donor. So that means that if this thing is doing its job well, meaning that it's strong, it's going to donate a lot of protons to make a lot of H3O plus. That means that the numerator is going to be bigger than the denominator, and you're going to end up with a K that is greater than 1. Let's go over to the camera here for a second. Does anybody remember? You guys might be too young to remember this, but there was a period of time, and this is really silly. Okay, I can't believe I'm going to end up posting this to YouTube, but anyhow, whatever. It's the land of the free. Does anybody remember in the rap videos? Like, I like rap music. And does anybody remember, and again, I might be dating myself, but there was a thing that you'd see in rap videos from time to time where they'd go, making it rain, and they'd take the dollar bills. And like, does anybody remember this? Give me a thumbs up if you remember making it rain. Anybody? No? Alexandria says LOL. Nobody. Okay, Luke, one person. All right. That's all. Oh, no, Clinton does too. Anyhow, so making it rain. So just using that concept, if you think about what's the function of an acid, it's to make it rain protons. The stronger your acid is, the more it makes it rain protons. Like, it makes it rain protons like crazy. Whereas if you have a weak acid, it's still a proton donor, but it's like, meh, I'm only going to donate a little bit of protons. So again, what's the function of an acid? It's a proton donor. So the stronger it is, the more it makes it rain protons. Is that good teaching or what? I feel kind of silly doing that. But does that help anybody understand at all? I don't know. Maybe it does, maybe it doesn't. All right, a couple of people. I'll take it. I like the emoji or whatever that is. All right, so let's go back. Oops. Son of a gun. How do I go back to sharing my screen again? Let's try this. There we go. Make it rain protons. So the function of an acid is to make it rain protons. So going back to this slide, again, the stronger the acid is, the harder the equilibrium is going to lie to this side, and therefore your numerator is going to be big, and you end up with a big Ka. Does that clear it up for anybody? I sure hope so. So anyhow, making it rain. All right, anyhow. Kind of a silly way of thinking of it, but hey, anything that helps you remember is great. All right, well, let's talk a little bit more about this Ka. And if you actually evaluate and calculate the Ka for strong acids and weak acids, you can see that Ka can have a huge range of numbers. Ka can be as small as 10 to the negative 50, and Ka can be as large as 10 to the power of 10. Now, I can tell you right now that Mr. Dion would be the first guy here to lose track of all those zeros. If I had to do 0.000000, 49 times or something, I would lose track. And so when we have numbers that are very small or very big, they're hard to work with. What do we do to alleviate some of that pressure or some of that stress? Instead of using Ka values, which can have such huge numbers, we use pKa values. And you would remember that, you remember pH, for example, is the negative log of the concentration of H+. That's something you should have memorized from general chemistry too. Well, pKa is just the negative log of Ka. And so instead of having numbers that range from 10 to the negative 50 to 10 to the power of 10, then we have negative 10 for a pKa all the way up to positive 50. And so the lower the pKa, the stronger the acid. I'm not going to review logarithms right now. So this would be a very strong acid if it has a low pKa. And if it has a high pKa, it would be a very, very weak acid. And thus the stronger acids, like HCl, for example, has a pKa of -7. Sulfuric acid, I think, is -9, something like that. So negative numbers, really strong acids. And if you're wondering, well, will I have to memorize any pKa values? The answer is yes. You will have to memorize some pKa values. And I have some of those shown right here, and I have some more over here. Let's just take a look at this. This is an artifact from a previous semester where I said it's on the inside cover of your textbook, but there is a table in chapter 3 that covers pKa's. However, a couple of things that I need you to remember about log units are that each pKa unit represents a magnitude or a power of 10, an order of magnitude, I should say, or a power of 10. That means that if you're comparing, let's say, sulfuric acid, which is a pKa of -9, and HCl, which has a pKa of -7, what's the difference between -9 and -7? It's 2. Okay, if you take -7 and you subtract -9, what do you get? You get 2. And so if you have 10 to the power of 2, that equals 100. And what does that mean? It means that sulfuric acid is 100 times stronger than HCl. If the difference was, 6 pKa units, then it would be 1,000,000 times stronger or weaker, depending. All right, so if we look at, some pKa values here, another thing that I need you to remember from your general chemistry days is that the stronger your acid is, the weaker its conjugate base is. Okay, that is a big thing you got to remember from your general chemistry days. Going down to the other end of the spectrum, the weaker the acid, the stronger the conjugate base. And thus, you can see the trend here for all these different pKa's as we go from sulfuric acid. So this is just H2SO4, it has a pKa of -9. Then you go to an oxonium ion, which has a pKa of -7.3. Then to hydrochloric acid, which is -7. Then you go to a hydronium. So this is H3O plus, of course. It says -1.74. As long as you know it's around -2, that's close enough for me. We'll just put that in brackets. Then you go to a carboxylic acid. So a carboxylic acid has a pKa of 4.75. As long as you know it's around 5, that's usually going to be good enough. The next one is called a 1,3-dicarbonyl. We don't look at those a ton in this class. However, they are going to come up a little bit in this chapter. And that has a pKa of around 9. Then you go to phenol. So this molecule here, this is an alcohol, but it's attached to an aromatic ring. So this is called phenol. And it has a pKa of 9.9, as long as you know it's 10. And the mnemonic my students have taught me is phenol, right? You have OL like this, and it kind of looks like a backwards 10. I know some people might find that handy. Next one is water, which is 15.7. If you read the textbook before coming to class, you probably would have noticed that it says that the pK of water is disputed. People say that it's actually lower than 15.7. It might even be around 14, but we'll just use 15.7 in this class. Then you have ethanol, which is 16, terbutyl alcohol, which is 18. And if you're thinking, do I have to memorize all these? The answer is, first of all, yes. But again, the take-home message from this table, table 3.1, is that a stronger acid has a weaker conjugate base, and a weaker acid has a stronger conjugate base. A more complete table that you will need to memorize is this one here. So this is the table that's found in your textbook. Memorize Memorize all pKa's. We'll just put here, memorize table. That'll make it a lot simpler. Memorize table. You need to know all of the pKa's on here. They have to be at your fingertips. So let's review. We're kind of starting off where we were on the last slide. Sulfuric acid, again, -9, so it's really strong. Then we call this an oxonium. It's -7.3. Then you have hydrochloric acid, -7. This is the hydronium ion. -2 is what we said. The next one is a carboxylic acid, which is around 5. Excuse me. The next one is a 1,3-dicarbonyl. So this is called a 1,3-dicarbonyl. That's around 9. Next we go over to the phenol. So our phenol, which is an alcohol attached to an aromatic ring, is around 10. Next we have water. Of course, everybody can identify water. If you're wondering, what's the difference between these alcohols, we're going to get into that. But this one here is ethanol. This is ethanol that's found in, beer and schnapps and wine, and, it's an additive in gasoline. This is another alcohol. I'll get into the name of the next one later. This molecule here is acetone, which is nail polish remover. It's also found in the paint thinner section at Home Depot. It's got a pK of around 19. So again, as long as you know it's 19, that's close enough. This one is the functional group here. This is an alkyne. So a terminal alkyne has a pK of around 25. This one is an amine. And of course, this is just plain old ammonia, NH3. But an amine has a pK of around 38. This is an alkene. Alkene has a pK of around 44. And the last one is an alkane. Alkanes are extremely weak acids. They have pKa's of 50. You can imagine that their conjugate bases are just super strong, okay, extremely strong. There's one other pKa that's not shown on here, and I'm going to throw it in and say you have to know this one too. It's right around here. It's the pKa of benzene, or an aromatic ring. So any one of these protons on here has a pKa of around 43. We'll put here pKa around 43. And so how would you memorize this table? You could use flashcards. You could, write it down over and over to help you memorize it that way. However, well, I think the best way to do it is, maybe do that flashcard thing, or, writing it down, just try to memorize it a little bit. But then if you put it into practice, if you start working on practice problems, and let's say I ask you a practice problem where you have to compare pKa's of 2 of the species in here, that's going to help you memorize it, and it's going to help you solidify your understanding of acids and bases even more. So that's my recommendation. All right. And this is just another slide summarizing something that I've mentioned twice already, that the stronger an acid, the weaker its conjugate base. And so if we go back again to something like sulfuric acid, which is a very strong acid, its conjugate base, son of a gun, where was I? Its conjugate base, okay, which is the HSO4 minus ion, so the hydrogen sulfate ion, that is a really weak base. Whereas if you go up to something like an alkane and you look at its conjugate base is extremely strong, because an alkane is a super weak acid. Give me a thumbs up if you follow me on the idea of acids, bases. Strong acid produces a weak conjugate base, and a weak acid produces a strong conjugate base. Again, this is review from general chemistry. And do I expect you to remember every single thing that you ever learned in general chemistry? Not exactly, and that's why we're going over it right now. Okay, well, it says here propranolol is an antihypertensive. Identify the most acidic proton in the compound and indicate the approximate expected pKa. And if you're going, well, hold on, whoa, Mr. Dion, you didn't show me this compound in that table. No, but I showed you the pKa of an aromatic proton. Right? These are all aromatic protons. If I fill in all these, so we know that the pK of an aromatic proton was around what? Can anybody tell me? I scribbled it down there at the end. What would the pK of an aromatic proton be? Yeah, exactly. So all these blue protons have a pK And even if it's not exactly 43, even if it's only off by a little bit, we're still going to have big enough differences that we should be able to figure it out. What about an alcohol? So this is an alcohol here. And therefore, so we'll put pKa of an alcohol. Let's go back to the table. Back to the table here. And if we look at these two here, these are both alcohols, ethanol, and this one here, which is terbutanol. One is 16, one is 18. Let's just pick a number in between. And if you want to put a range, that's fine. You're still going to end up with the right answer. Let me show you. Let's go back here. Let's just write pKa of 16 to 18, somewhere in that range. What else do we have here? We have an amine. Okay, so we have an amine. What was the pKa of an amine? Could anybody tell me that? You go back to the table, or if you look in your textbook. Anybody? The amine, if we go back here. So here's an amine. So the pKa of an amine, exactly, it's around 38. Yep. So let's scribble that in. Go back here. So the amine had a pKa that was around 38-ish. And that's about it. And if you're wondering, well, hold on, Mr. Dion, there's a bunch of other protons. You have 2 here. You have 1 here. You have 2 here. You have 1 here. You have 3 here. Okay, you have 3 more here. But all of those protons that I have highlighted in black, they're all on sp3 hybridized carbons. And this is the only thing that we saw that was a proton on an sp3 hybridized carbon-hydrogen bond. So that means it's around 50 for all of those protons. Again, it might be slightly different. It might be a little bit lower for some of them, depending. All of those are around, we'll just put here, pKa is around 50. And therefore, the answer is going to be this proton here would be the most acidic proton in the molecule. It's got the lowest pKa by far. You see that nothing comes even close to this. The closest thing to it is what? The amine, which is 38. If you take 38 and you subtract 18, you get 20. So that means the difference in its relative acidity between the hydrogen that I have circled in red and the one in green is 10 to the power of 20. I don't even know what that number is, but it's really big. 1 with 20 zeros after it. And therefore, this proton is much more acidic than any other proton in this molecule. By far and away, it is much more acidic. Give me a thumbs up if you follow me on that question and how I applied the table to identify those. So therefore, you can see why it's so important that you know functional groups. That's why we look at functional groups at the very beginning of the class, okay? Andrew, which one of these protons has the lowest pKa? That is going to be the one that is the most acidic. So which one has the lowest pKa? It's the one that is highlighted in yellow. Therefore, it is the most acidic by a long shot. It's not even a contest. Because the hydrogen, if it's attached to an sp3 hybridized carbon, this is sp3, right? If we go back to the table, the only time it shows up anywhere in here, any of these red protons attached to an sp3 hybridized carbon is the alkane. And an alkane has a pK of around 50. There you go. All right, well, let's move on. And let's see if we can identify the stronger base in each of the following cases. How would we identify which one is the stronger base? What we're going to do is we're going to look at the conjugate acid. Whichever one is the weaker acid is going to produce the stronger base. So since both of these have negative charges, you see if you go back to the pKa table, okay, there is none of that. Remember, you're memorizing the pKa. Okay? The pKa values all correspond to the acids, not to the conjugate bases. But again, we know that the stronger the acid is, the weaker its conjugate base. And the weaker the acid, the stronger its conjugate base. Therefore, if we go back here, what we can do with both of these molecules, or these ions rather, is draw their conjugate acids. How would you do that? You add a proton. If you add a proton to this carbon, right, if you add H plus, you end up with this molecule. Okay, so you end up with an alkyne, and if you add H plus here, so plus H plus, you end up with NH3. What were the relative pKa's? The pKa of this proton on an sp hybridized carbon. Can anybody tell me what the pKa of this proton that I have circled in red is? It's on the table, I swear. In fact, that exact molecule is on there. Yes, it's 25. This has a pKa that's equal to 25, excuse me, where this proton has a pKa that's equal to 38. The stronger acid is going to produce the weaker base, and the weaker acid is going to produce the stronger base. And we'll put here weaker acid, therefore stronger base. All right, so we solved the first one. Didn't give myself a lot of room here, didn't I? So if I divide this kind of like this. Okay, for B, if I call this one A and I call this one B, could anybody identify which one of these would be the stronger base? Would it be A or B? You can go back to the table. Which one would be the stronger base, A or B? Excuse me. Yeah, exactly. A is going to be the stronger base. How did my students know that? Let's delete this. This is the stronger base. How do we know that? If we add H plus to this guy, we end up with this molecule. And if we add H plus to this, we end up with this molecule. If we compare the relative pKa's, we saw that the pK of this molecule was 18, and the pK of this molecule was 16. Again, same rationale. We'll put here weaker acid, therefore stronger base. All right, we just compare the acids and bases. So whichever acid has the higher pKa is going to produce the stronger conjugate base. Whichever acid has the lower pKa is going to produce the weaker conjugate base. Okay, let's try another one. Let's go over to a blank document here. Excuse me. And let's just come up with one here. Let's see. What if we did something like, let's see. If we were to compare, we're looking for stronger bases. Yeah, so stronger base, question mark. What if we compared acetone versus water, H2O? Could anybody tell me which one of these would be a stronger base? Would it be acetone or water? You'll have to go back to the table. So we're looking for the stronger base. Okay, let's draw the conjugate acid of both of these. The conjugate acid of this was the oxonium. Okay, the oxonium ion, and the oxonium had a pKa that was equal to -7. The conjugate acid of water is hydronium. This, and hydronium has a pKa of around -2. This is our stronger acid. This is the weaker acid. Therefore, the conjugate base of the weaker acid is going to be the stronger stronger base, and this is going to be the weaker base, and therefore the stronger base would be water if we compare acetone and water. Let's try one more, and then we'll move on. Let's try, if we were to compare, and again, we're looking for the stronger base, your stronger base with a question mark. If we compared CH3, CH2 minus versus this ion, okay, both of these carbanions, if we compare the two, which one would be a stronger base? If I call this one A and I call this one B, which one would be a stronger base? Excuse me, sorry. Yeah, absolutely. Thanks, Kiana. It's going to be A that is the stronger base. How did she know that? Well, we look, and if we add H plus, we end up with CH3, which is an alkane. Now, an alkane has a pK of 50, whereas if we add a proton here, we end up with we end up with this guy, and this has a pKa that is equal to 25. Weaker, sorry, I got bases on my brain here. So stronger acid, we'll hear weaker acid, therefore stronger base. Done. All right, so what do you need to do? You need to review the table, you need to memorize the table, and then you need to practice identifying acids and then be able to compare the relative pKa's and then evaluate, okay, well, which one of these is stronger, which one of these is weaker. Let's go back to the lecture slides here just for a sec. And let's try a problem here. It says, or sorry, let's move on to a new concept rather. It says using pKa values to predict equilibrium. This is another one of those, bombs I'm going to drop on you that you've got to memorize this. Okay, we already saw that the equilibrium, or we saw pKa values. So we looked at low pKa means a strong acid, high pKa means a weak acid. But when we're looking at an equilibrium, it says with relevant pKa values that you memorize. So memorize the table. We'll put here table 3.1. You can predict the direction of an equilibrium, and you can determine which side of the equilibrium is going to be favored. And what you need to remember is that the equilibrium, is always going to favor the side of the weaker acid. Always favors the side of the weaker acid. Sometimes students will get it in their head. Well, they say, well, if it's stronger, then it should lie on the side of the stronger acid. Yeah, strong. Strong is good. Strong is powerful. So we should have more strong acid. No, because what's the function of an acid? An acid makes it rain protons. So the stronger the acid is, the more it's going to do its job and make it rain protons. Thus, if we compare these two acids, if you compare water as an acid and this alcohol as the conjugate acid, since water has a lower pKa, it can make it rain protons more, so it lies to the side of the weaker acid. And that's why we write the equilibrium arrows in this way, where you see that this one, the one that's pointing to the right, is bigger. So equilibrium, it's trying to tell you the equilibrium lies to the right side. Right, here we go. Okay, so the equilibrium is always going to lie to the side of the weaker acid. Why? Because the stronger acid is doing its actual job. It's making it rain protons, and therefore it's going to push harder. Right? You can think about two people pushing against each other. This person is strong, this person is weak. Which side is it going to lie to if they're both pushing against each other? It's going to lie to the side of the weaker person. Right? They're going to start going towards the weaker person because the weaker person doesn't have enough force to push the equilibrium towards the side of the stronger person. Maybe not the best analogy, but it's definitely not the worst. All right, let's move on and look at one more concept here before we take a break. If you take a look at this reaction, you have your base. Let's look at this very carefully. This is our base. This is our acid. This is our conjugate acid. This is our conjugate base. The base is attacking the acid and taking the proton, the pair of electrons that we were using to bond the hydrogen to the oxygen and water. That bond is being broken, and that pair of electrons ends up on the oxygen to make a hydroxide ion. If we compare the pKa's of the acid and the conjugate acid, that's what we do. The pKa of water is 15.7, and the pKa of this molecule, which is butane, anyhow, its pKa is 50, right? Again, because this is an sp3 hybridized carbon. Which one is weaker? Well, definitely this one is much weaker acid. You can see the difference in pKa values is 34, so that's 10 to the power of 34. That's a huge amount. It's going to lie to the side of the product so hard that we don't even write a reversible arrow. We just say the hell with it. Okay, there's going to be none of this left over, right? Everything's going to end up as being butane and this hydroxide ion. And there we go. So the equilibrium is going to lie to the side of the weaker acid. Now, if you're wondering, well, what if I get something, what if you show me a base that I haven't memorized? Or what if I go blank on the table, if I don't have it memorized perfectly? Can I do a qualitative treatment or a qualitative assessment of a molecule and say, well, this would be a stronger acid, this would be a weaker acid? There is a technique that you can use to qualitatively look at an acid or a base and determine its relative strength. And the acronym that we use is ARIO. And ARIO, A-R-I-O, represents the 4 steps that you take to assess, which base is going to be more stable. The A stands for atom, R stands for resonance, I stands for induction, and O stands for orbital. And we use them in that order. We start with atom, we go to resonance, we go to induction, and finally, we look at orbital. And again, we use this acronym to compare the relative stability of bases. Okay, so not acids. We're looking at bases, but we know that the more stable a base is, the stronger its conjugate acid, and the less stable a base is, the weaker its conjugate acid. And that's what we're going to look at after our break.